When a massive earthquake strikes a major city, you might expect the tallest, heaviest skyscrapers to be the first things to fall. In reality, these giants often ride out the motion, while the shorter, stiffer buildings around them shatter into debris. Historically, structures built to feel solid and invincible failed under the immense lateral forces of a shifting tectonic plate. This destruction is driven by the secondary, or S wave. As these seismic waves travel upward, they translate into violent horizontal shearing motions at the surface level. The primary threat to a modern tower comes from the massive payload of kinetic energy these lateral waves inject into the structure's foundation. Every structure has a natural period, the seconds it takes to naturally sway back and forth, modeled here as a mass on a column. Danger arrives when seismic waves match this period. Resonance causes kinetic energy to compound, increasing oscillation amplitude with every cycle. This conflict is intensified by inertia. While the ground shoves the foundation sideways, the upper floors try to remain at rest, creating massive internal stress. Relying purely on stiff, unyielding materials for a skyscraper's frame guarantees destruction under these resonant forces. To stay standing, engineers must trick the physics of the quake by intercepting, absorbing, and dissipating that energy before it reaches a breaking point. The first line of defense begins at the very bottom of the tower. This is base isolation. Instead of being anchored directly into the bedrock, the building sits on flexible bearings. These isolators stretch and compress to absorb the lateral shear of earthquake waves, allowing the structure above to float in place. By acting as a physical firewall, base isolation denies the majority of the earthquake's kinetic energy entry into the structural frame. Even with isolation, some kinetic energy will inevitably bypass the foundation and transfer into the building's skeleton. Rigid resistance is a flaw. A brick wall shattering under impact contrasts with a bamboo stalk smoothly yielding to force. Engineers mimic this property using high-tensile steel frames, allowing the building's core to bend and deform without snapping. This flexibility allows the tower to safely spread the kinetic energy throughout the structure, exhausting the force through movement rather than failure. At the top of a skyscraper, the swaying motion is at its most extreme, threatening the integrity of the entire structure. To stabilize the summit, engineers install a tuned mass damper. This is a multi-ton pendulum suspended near the roof, surrounded by hydraulic shock absorbers. As the building sways to the right, inertia causes the massive pendulum to swing to the left, acting as a dynamic counterweight. This system continuously swaps kinetic energy between the building and the pendulum, which dramatically reduces the amplitude of the oscillation. The damper acts as the final shock absorber, actively counteracting the earthquake's rhythm to restore the building to equilibrium. The Taipei 101 tower stands as definitive proof. Its 660-ton golden damper successfully neutralized the motion of the massive 2008 Sichuan earthquake. In Los Angeles, the Wilshire Grand Center utilizes a central core with heady steel bracing to distribute seismic energy evenly across a major fault zone. And Mexico City's Torre Mayor uses dozens of viscous dampers to survive the extreme resonance caused by the city's soft soil foundation. These buildings remain standing because their engineers mapped and anticipated the flow of seismic energy before the ground ever moved. Once the massive kinetic energy of the earthquake is completely exhausted, the skyscraper settles back into a perfect vertical alignment. Structural survival relies on a deliberate shift from rigid resistance to dynamic adaptation. By integrating flexibility, isolation, and active damping, engineers transform a violent seismic event into a series of controlled, harmless vibrations. Designing skyscrapers to move in sync with the shifting ground has turned the world's tallest buildings into resilient icons capable of enduring the raw power of our planet.